Hi everybody, it's Mr. Spook again, and today we are talking about vectors. Now you might have reviewed vectors versus scalars earlier in the year, okay? But I'm going to cover everything right now because we're about to move into projectile motion. And with projectile motion, it will be objects that have both a vertical velocity and a horizontal velocity. So being able to keep track of both is really important. So moving into vectors, let's talk about a few terms you need to know. All right. The first one you need to know is magnitude. Magnitude just means any number. It just means the value. Okay. Magnitude is sometimes can be the absolute value of something as well. Okay. Because again, when we talk about what's negative in a physics class, negative just means direction. So magnitude, any type of number, whether it's a scalar or a vector, it will have a magnitude. Okay. What a scalar does not have is a direction. Okay, so the word scalar is talking about numbers and values that do not have a direction to them. All right, so time would be a scalar. Speed would be a scalar. So these are numbers that don't have a direction to it. Now, a vector has to have the magnitude as well as the direction. All right. So when we talked about velocity and we compared velocity versus speed or displacement versus distance, right? Velocity had both the magnitude and the direction, which is why it was different or how it was different than speed, all right? Also, when you hear the word vector, you're going to know about these arrows. And arrows is just a way to draw the picture where we have a nice arrow, we draw, and it will represent the vector we're talking about. So if you have a longer arrow, that would mean it's going to be a higher value, higher magnitude. And it also, the direction of that arrow is going to be important. Okay, so vectors will be, we're going to compare what a vector is to a scalar here for a little bit. And then we're going to show how the math is used for these vectors by drawing out arrows. All right, so a few questions. What do you think? Just a quick guess. Scalar versus vector. Is distance a scalar or a vector? Distance is a scalar because it does not care about direction. All right, what about displacement? Displacement was a vector, right? And we compared those earlier in the year. Velocity? Velocity is a vector compared to speed, which is a scalar. Okay? Acceleration? Acceleration cares about direction. We've talked about gravity, right? Gravity pulls down. Well, that direction is important. So acceleration is a vector as well. Time is a scalar, okay? At least in this class. When you go to modern physics, maybe Einstein would say something different about that. All right, force. Well, the direction, we haven't even covered force yet, but direction of force is important. So force would be a vector as well, okay? All right, now a couple more definitions. Now let's talk about the actual arrows. Some terms that you need to know. First one would be components. So any components will be the arrows that will always be perpendicular to each other. So they can only be, say, horizontal and vertical, or east or west versus north and south. But components will always be perpendicular to each other. And we draw these components tip to tail. Okay, if you notice in the picture, the tip of arrow A is touching the tail of arrow B. We could have a ton of components, all right? All kinds of components going around, and we need to draw all of them tip to tail. That is a number one rule for drawing components, okay? Components could be used to break down an arrow that's on an angle. Components could also be used to add things up together to create one big vector, which we call the resultant vector, okay? So the resultant vector is going to be the one final arrow, all right, that will have obviously a magnitude and a direction, and we always draw that arrow start to finish, okay? So that one is going to go against the rule of components. It's not a component, so it will not be tip to tail. The final resultant arrow will be start to finish. And the way I want you to think about it is just what makes common sense for direction, okay? So if A and B, let's say A was me walking to the east 5 steps, and B was me walking north 3 steps. Okay, so if I went 5 steps to the east, 3 steps north. Well, what should be my resultant direction? Should be northeast, right? So if you follow the resultant rule of start to finish, you should get an arrow that's going to be pointing northeast. A common mistake that students will make is draw their resultant tip to tail as well. Okay, and if we made that mistake with this triangle, you would see arrow Z not pointing northeast, you would see it pointing southwest. Okay, so those are the rules. Components are tip to tail. Resultant is start to finish. Okay, and obviously if you're seeing a right triangle, you're seeing that you're about to possibly use a Pythagorean theorem to find the resultant, or at least the magnitude of the resultant. All right, so this is what I want you to do. I would like you to try to draw this, what happened here, okay, with following the rules of components. All right, so this is what we did. Let's say that I walked 5 meters north, then I walked 4 meters east, then I walked 7 meters north, then I turned and went 8 meters west and 2 meters south. Using our rules for components, I would like you to draw those components together on your paper. Go ahead and do that now. Okay, are we done? Should I wait? No? Okay. All right, so let's see what that picture should look like. That picture should look more like this. Okay, so we have our red arrows following our components. And so we have our 5 here, then we have our 4, then we have our 7, all right, then our 8, and then our 2. All right, now to figure out the resultant, you obviously knew to draw start to finish, and that's what our arrow should look like. But how could we do that with math? Well, what I strongly urge all of you to do is anytime you deal with vectors and you're dealing with at least, or let's say more than 2 vectors, draw those vectors, but also list them in columns. List anything that's east or west in one column. List anything that's north and south in another column. It might not be east-west, it might be vertical and horizontal, but it's the same idea. Use columns to keep track of your components. Okay, they have to be perpendicular components, but use columns to keep track of it. So if I do that here, I see a 5, so I'm going to write a 5 in the north here. All right, it's an ugly 5, but it'll work. Then I have my 4 east. Then I have my 7 north. Okay, my 8 west. What do you think's wrong with me just writing an 8 there? Well, we've said with vectors, direction is important. And if I've already said that 4 is positive, then I need to make my 8 negative. So I'm going to have a negative there. Okay? And finally, we have a 2 going south. Same thing. With the 2 going south, I'm going to make that negative because I've already said that north is positive. Okay? Now, the reason I do that, one, it's just going to help with our organization. But then if I wanted to figure out the length of this blue arrow, okay, I first would need to add or get the sum of each column. So if I have a 5 and a 7, okay, minus a 2, I'm getting a 10 over here, right? 5 plus 7 is 12, minus 2 is 10. All right, on the other hand, in the east side, I have a 4 and a negative 8, which is going to give me a negative 4. So now I have my components. My components, if you look at that arrow, that means I have a component that I could redraw on here. And this component would be a negative 4 horizontally, or negative 4 east, or we have 4 going to the west. All right, and we have 10 going north. And maybe you see it, hopefully you do, but I've just recreated a right triangle there, which I could easily do Pythagorean theorem to get the answer for. Okay? All right, now, what about these 2 arrows? With these 2 arrows, they are no longer perpendicular. Okay, so if I wanted to find the resultant here, there's going to be a few steps I need to do. Okay? First off, what is the rule that is being broken with these 2 components? There's a couple of them, but what's one rule that is being broken with these two components? I'll pause it here and you answer that question. Okay. Did you guess that one of the rules broken is that our components are not tip to tail? Because they're not. Okay, they're tail to tail. So let's take care of that first. And then if you said instead that they're not perpendicular, you're absolutely right, and we'll take care of that next. Okay, so let's make them tip to tail. There you go. Okay, you can move arrows however you want to move arrows. So if you do have arrows that are not tip to tail, you can do whatever you want to move them. Think of them as a computer where you can click and drag those arrows, but you cannot change the direction of those arrows. So when we move components around, think of it as something you can click on and drag, but don't try to change the direction of them. Okay, so now we have these components tip to tail. All right, but they're not true perpendicular components. So what we would need to do next is get the perpendicular components of them. All right, we won't do the math right now for it, but I'm going to get my components, and you would be doing some SOHCAHTOA in there to get those components. Okay, now do you see that A and C are both going in the same direction? Okay, and B and D are both going in the same direction. So now we have components that are perpendicular to each other. All right, same thing we want to do. We still have our columns. So instead of east and west or north and east, I have vertical and horizontal. It doesn't matter what you do. Okay, depends on the problem, but however you want to do it, as long as they're perpendicular. So I list my B and my D because those are vertical components in the vertical column. And I list my A and C in the horizontal column, and there we go. Okay, now you would do the same thing with the numbers. Let's plug in some numbers with these. Oh, real quick, look at that. That's what our new resultant would be. Remember that our resultant would be one final arrow. It would have to be start to finish. So in this case, we had two arrows that are going northeast at different angles. So we better have an arrow that ends up pointing northeast. So that's what my component would look like. Okay, now let's plug in numbers. All right, so plugging in numbers, let's say we had a 5 and a 5 horizontally, we'd list those in the column. We'd get the sum of those. We have a 1 and a 4 vertically, we list those in a column and get a sum. Okay, and then to find that big large red arrow, hopefully you see that we've just created a big right triangle. Okay, so arrow C, the red arrow, is the hypotenuse of our new big right triangle, and we can use a Pythagorean theorem. All right, now I will say that for my class, this is where we would push the envelope with the problems. I might give you a problem like this, and this would be something expected, where say I give you two arrows, and maybe I give you, I'll move back for a second, maybe I'll give you something like this to start with, okay, and give you the values, the resultants, and angles of these two arrows, and have you break it down step by step to get that final arrow. Okay, so that would be a goal for you in this class, is if you could do that. All right. Here are some math tips to remind you of. I won't go through everything. I won't reteach SOHCAHTOA to you here, okay? But I will tell you this. One, in physics class, we can kind of limit down and almost make a cheat sheet for our math with Pythagorean theorem. And that's because this. If I give you, in a physics class, if I give you or either I'll give you a velocity and an angle, which means I give you the resultant and the angle, or I'll give you the horizontal and the vertical components. Okay, so it's really going to be an either or. All right, I might give you the horizontal and vertical components. Maybe you have to get a bunch of them, but there'll be horizontal and vertical components, and you need to find the hypotenuse. Or I'll give you the hypotenuse or the resultant, and you have to find the horizontal and vertical components. Okay, so a quick little cheat is that you can, if you're ever going to be getting components, it will always be the hypotenuse times the sine of the angle, and then the hypotenuse times the cosine of the angle. All right, so that's why I have the vertical component in physics class. every time we deal with angles with projectiles, the angle will be with respect to the horizontal. Okay, meaning it's going to be if this is the horizontal, how many degrees up from the horizontal. That's the way we deal with projectile motion. Okay, it won't be the other angle. So we know that it's always going to be the angle with respect to the horizontal, as you see here. Okay, so that means we will always be doing h sine, or the hypotenuse times sine of the angle, to get the vertical component, and the hypotenuse times cosine of the angle to get the horizontal component. Okay? Now, if you're going the opposite way, if you are given your components, they will always be horizontal and vertical components. To find the resultant, you'll be doing the Pythagorean, right? A squared plus b squared equals c squared. And to get that angle, you will be doing inverse tangent, okay? And your math teacher might call it, I believe, arctangent. I'm sorry, but I always say inverse tangent. But that's how we're going to solve it. So if you are ever needing to find the angle, it always is going to be with respect to the horizon in a physics class, okay? You will be doing inverse tangent of your opposite, which is your vertical, over your adjacent, which is your horizontal, okay? All right. Really, that is it for me. Thanks so much for watching, and I'll see you next time.